What I want to talk about today is vibrations, and it's going to be mainly about particles, and it's going to cover free vibrations in a little bit more detail than I have before. So in terms of the learning objectives, I want to go over some of the derivations for undamped free vibration. Look at energy methods, which are not part of the course, and I understand that, but I think it's actually kind of a fun way to do things, and I sort of throw that in because it's not that hard. Undamped force vibrations, which is another one, and I don't touch too much on damped force vibrations other than to sort of say, well, they're there. We talk about viscous damped free vibrations and electrical circuit analogs. Okay, so we've had three cases so far. Those three cases are the kinetics. Sum of forces equals mass times acceleration. Great, I know that one. So that's there. Work energy, mv dvds. Okay, no problem. These are great because it's easy to follow. And then finally I have momentum, which is force, velocity, and time. So acceleration, velocity, and distance. Force, velocity, distance, and then finally force, velocity, and time. So let's consider force and displacement. So rewriting this equation not very much differently than usual, but as mx double dot. And so the goal here is to take these ideas, take this sort of approach that we're going to have in this chapter, and just look at that second law equation. Vibrations, and it's always good to have a definition, is vibration is a periodic motion of a body or system of connected bodies displaced from a position of equilibrium. We're going to have two different cases. Free vibration, motion is maintained by gravitational or elastic restoring forces, conservative forces, or we're going to have external periodic or intermittent forces applied to the system. And so the typical case is, say, a mass on a spring, and it's just going to oscillate up and down. Both can be damped or undamped. We'll talk about what those are later. But let's start with the first one. A block that is horizontal, so there's a floor underneath this mass. It's released from a displaced position x, and the spring is going to want to pull back on the block, and it's going to cause a vibration that's going to move back and forth. So something like this. This is what I kind of expect. And the block will move out of equilibrium when x equals 0, and for now, oscillation, as far as we're concerned, will continue indefinitely. So acceleration is proportional to displacement. So I have simple harmonic motion of force equals kx in this direction. And if I was careful, I would have written my x and y coordinates here. And so if I do the sum of forces in the x direction, it's really just going to be the spring force minus kx equals mx double dot. And I'm going to write this as x double dot plus k over mx, which will equal x double dot omega squared n x. That's omega n kx. And there'll be two possible solutions. X is equal to sine of omega n squared t, or omega n t, or plus b cos omega n t here. So great. That's a good solution, and it has the advantage that it will continue indefinitely. That is, it's a sine and a cosine, and I can put in any type of boundary condition here that will work for this particular case. I can use a second definition where I just leave it in terms of sine plus a phase difference, so a phase lag of phi. It's the equivalent to the equation just above, but it's a little bit more compact and easier to work with. It's not anything special in terms of how it looks. In fact, honestly, I kind of find this expression a little bit easier to operate with. If you solve these problems, you typically have some sort of initial condition. Typical in this course are x position at 0 is equal to x naught, v naught equals 0. You then substitute in terms. So if you say x at 0 is equal to x naught, then you have a sine omega nt, which goes to 0, b cos omega nt, which goes to 1. So it's b equals x naught. If you say v is equal to x dot, and then you get v naught is equal to, because this cosine term remains, this sine term goes away, a is equal to v naught divided by omega n. And often you find that these are relatively simple equations to solve, to set up. And really, we often ask you just to set them up, not much more than that. But it's really doing the force balance that's challenging. You also can have solutions that look like this, where you say, well, x is equal to xm sine omega nt plus phi, or x is equal to c omega nt plus phi. And xm is just going to be the amplitude that you calculated in the previous part. So these are not, there's no real challenges to these problems. You're going to get used to them. You'll see a lot of them. But the really important thing is that you start to practice them. Phi is just the phase angle, so it allows that the sign at 0 not necessarily be 0, so that if you're doing a problem where you have an initial displacement, that you can cover it. And that's going to be inverse tan of V naught over X naught omega n. And that's your phase angle. Tau n is the period, and it's just going to be 2 pi over omega n. Omega n, again, is the natural circular frequency, and that's the period of the vibration. The natural frequency is the inverse of 1 over tau n. It's omega n divided by 2 pi. So natural frequency is Fn. Natural circular frequency is going to be omega n. So often in these types of problems, often as you're dealing with all of this stuff, it's really important to start with standard sort of definitions and knowing what those definitions are. We don't do a lot in terms of derivation or explanation in terms of how you get these terms, but you really should be aware of what these terms are. Now then, the next approach that you can do with these problems, again, these are outside of the lecture, is to look at problems where you have, in fact, a set of conservative forces that are playing a role. So conservative forces, of course, in this course often mean just a gravitational or elastic spring forces, and these forces are conservative. So you can use conservation of energy equations to sort of extract that. So you displace the block x from equilibrium. Your kinetic energy is 1/2 mv squared, or writing it in the notation we're using here, 1/2 mx dot squared. You have potential energy, which is 1/2 kx squared, which you can just use directly, and you can start to add terms. So T plus V is equal to a constant, because you know that total energy is never going to change because it's conservative. You have 1/2 mx dot plus 1/2 kx squared. I can take the derivative of this with respect to time, and I end up with mx dot x double dot plus kx x dot equals 0. And I end up with x dot equals mx double dot plus kx. Now the trivial solution, of course, is x dot is equal to 0. We're going to ignore that, but I get the same operating equation, or the fundamental equation of motion, as I did before. Let's switch directions and make it vertical, because this is often a problem that a lot of people see, and it becomes a little bit more challenging to think about. Now, one thing you'll notice here is that I've changed the direction of motion so that the axis is aligned in x, because I like to write things as x. Y is in the horizontal direction. X is downward as positive. And so if I continue and remove my finger, the mass will move down and reach static equilibrium. It's pretty standard. Just do it slowly, make sure I don't have any oscillations, but it'll sort of move down and reach some sort of point. After I do that, I can say, well, the sum of forces in x is equal to k minus k delta x plus mg equals 0. Okay, so that's my static. Now, if I displace this by a small distance, delta either up or down, my equation becomes minus k delta x plus delta plus mg equals max. Now, what's interesting about that is these two terms cancel out, and I end up with minus k delta equals max. Well, that's my static equation, and I already know right here that it's equal to 0. So my dynamic equation is looking a lot like the term I had before. And so I can rewrite that and say, well, mass ax minus k delta equals 0. Using the coordinate system I have, say mx double dot minus kx equals 0. And I end up with the same expression as I had for the horizontal motion. And so if you think about it that way, you suddenly realize that you can do a lot of things with these, and you can do this also with energy as well. So the important thing here is to understand how these equations are sort of done and derived, and the fact that I can refer to things as static solutions and dynamic solutions. I wanted to do one example from Meriam and Kraige. This is 8.6. Determine the natural frequency in cycles per second for the system shown. Neglect the mass and friction of the pulley and assume that the block of mass m remains constant. So if I draw one of my drawings of this, I know under static condition the system is not moving. So I have made a mess here. If I drop by delta x, the cord has no extra length. And the only place that the cord can stretch is the spring. And so if this goes down, or this moves by LA and LA, this has to move by 2 delta x in order to make up for the loss in length, or the increase in length of the cord, because this cord sort of starts here and ends here. It's sort of a finite length. I can see that with my eye. So to take care of that, the spring is actually responsible for all of the distances, which means that under static conditions, my system consists of 2kx, 2kx going up, mg, which is mg here. So 4kx minus mg, which equals 0. And again, downward is my direction of motion. Total solution for the motion is x static plus x dynamic, which is the same thing as we just did a moment ago. And if you do that and you sort of put in the terms and you substitute all the expressions and have mg, you end up, after eliminating all of those static terms, with minus 4kx equals mx double dot. And again, remember, it's the original solution will have x static plus a delta, and I'm just going to refer to it as x. I end up with a dynamic equation. The equation of motion is x double dot plus 4k over m x equals 0. And I can substitute in terms, and I get omega n is square root of 4k k over m equals 2k over k over square root k over m. But they ask for the natural frequency. This again, natural circular frequency. And so omega n over 2 pi equals 1 over pi k over m, because that 2 is going to cancel on the top and the bottom. Let's look at undamped force vibration. So same system, same block. Whoop. And I have here a system that, again, it's on a floor. But I've added a forcing frequency of f naught sine omega naught t. The force has an amplitude of f naught and a forcing frequency of omega. So in undamped force vibration, we do the same thing. So we're just going to draw the free body diagram, solve for the forces, solve for the motion. We get a non-homogeneous second order differential equation. And there'll be the difference is we're going to have a complementary solution and a particular solution. And the complementary solution is going to be the solution for the case where this term goes to 0. The particular solution is that this term, no, sorry, not this term. This term goes to 0. And the particular solution will include the forcing frequency. So I end up with this term right here. And so again, if I'd written it on the right line, this is 0. I have x characteristic, which is now going to be in terms of the natural frequency, a sine omega nt plus b cos omega nt, and the particular solution sine omega naught t, because this is sine omega naught t2. Now these are a lot easier because I'm using forcing that is based on sines and cosines. You can do forcing on anything you want, square waves, triangle waves, and it becomes more challenging in terms of how you describe what's the forcing frequency. You can do random signals too. If you add everything together and you sort of put all the terms together, you'll get a final frequency or a final result that is 0. And you know that this term is going to give you, or this solution is going to give you f naught over m, omega n squared minus omega squared. And what you find is that you end up with a magnification term. That magnification term right here, which I just kind of added in, that particular solution is a bit of a pain in the neck, because suddenly you realize that as you approach the natural frequency, you start to have this thing shake apart. Now, in all likelihood, none of you are familiar with the 1970 Chevy Nova, which had a habit of shaking apart at around 100 kilometers an hour after it had about 20 years of service. But for those of us who were undergraduates at that time, all of us remember driving along. Once you hit the highway speed, it would just rattle your teeth for the next few hours until you reached your destination. And that was partially because you had achieved the natural frequency or close to the natural frequency, and the entire thing started to shake apart. And it would shake apart at that frequency associated with the forcing frequency, which might be, say, for example, if you're driving the 401, bumps on the road. So that magnification factor is 1 over 1 minus omega n squared, and it's something that people look at, especially when they're trying to do various types of analysis. So for example, I have a set of experiments I'm doing aerodynamic control, and I actually try and operate the control devices very close to a resonance frequency or a magnification factor so that I kind of achieve very high energy outputs from these devices. Next, viscous damp free vibration. So here I have no forcing. Damping is a resistance to vibration, so we tend to look at this as a viscous damping force. Again, now we introduce K, which is this thing here. We have the force that comes from the spring, which comes from the back. But now we also have this force from we have the damping force, which is Cx dot. It's going to go as a function of velocity. So if I do my free body diagram, I have force equals Kx in one direction. I have Cx in the other as well, and I should draw that in the same direction. So it's minus Kx minus Cx dot. If I add up all of the terms here, they equal to 0. And if they all equal to 0, I have mx double dot x dot and x, and my life becomes a little bit more difficult because very clearly I can't use my sine cosine solutions that I've spent all of this time developing. The solutions that I have to use are something that look like this, which are x equals e to the lambda t. Solutions have the form of lambda 1 minus c over 2m plus square root of c over 2m squared minus km, or lambda 2 equals minus c over 2m minus c over 2m squared minus km. Difference is the plus and minus right here. So if you have, so just again sort of circle that term right here. There and there. That's the only difference. The term underneath the square root is really important. C critical over 2m squared minus km equals to 0 is critical damping. And this is this case down here, and it will be a plus bt e to the minus omega nt. Over here, you have, if you don't have critical damping, you can sort of calculate critical damping as 2m times the natural frequency. If you have overdamped, you have a e lambda 1t plus b e lambda 2t. There's two solutions to this. In critically damped, you have x equals a plus bt e to the minus omega nt. In this case, you have two roots of the same value, and that's why you end up with a solution like this. In the underdamped case, you have x is equal to some constant times a logarithmic declination sine omega damping t plus phi. So if you do that, you can sort of put that damping factor in there, and you can relate it to omega n, the natural circular frequency, 1 minus c over cc, quantity squared. And you can have a period of the damped vibration, 2 pi over omega d. Now, one of the things that we always promise to talk about, and it's always met with great excitement, is the relationship between our course and electric circuits. So you have this equation, mx double dot plus cx dot plus kx, and it's going to be related to inductances, charge second derivative, resistance, charge first derivative, and current over capacitance. And there you go. A lot here, but keep in mind it's a standard form. You solve for forces. There are a limited number of standard solutions.
The best way to go through these problems, read the questions carefully. Look at what they are. Make sure you're aware of what's involved. You won't find them very difficult after a while, but they're very difficult about the first time that you do that. We looked at undamped free vibrations, energy methods, which are not covered in the course really, but I kind of like them, and I also talk a little bit about Lagrangian methods elsewhere. Undamped force vibrations, viscous damped free vibrations, and electrical circuit analogs. All of this together sort of gives you an overview of what to expect in this chapter. There's a lot of material here, and it's not necessarily very challenging, but it is new, and it's important that you get comfortable with it when you start. Thank you very much, and we will discuss more about this later.